Assalamualaikum warahmatullahi wabarakatuh and good day. So in this video, you will learn chapter 5, okay, a new chapter entitled Sampling Distribution and Estimation. Okay, so previously in chapter 4, you have learned function of random variables. Okay, so you have three methods there, how to find the function or how to find the probability distribution of a function of random variables. Okay, so this is a quite different chapter, which is sampling, distribution and estimation. But this one you have learned before, you have applied this concept before in applied statistics subject. Okay, if you remember in chapter 2, okay, confidence interval too. All right, so in this chapter, okay, sampling, distribution and estimation, this is the expected outcome. So you can see that by the end of this chapter, you should be able to calculate probability distribution for sampling distribution function of the observable random variables in the sample. So similar, all right, that's when you have population, you want to make inference about this population, but how you want to make inference using the samples. So these samples, you want to find the sampling distribution function of this sample. Okay, and then number 2, to understand and calculate the sampling distribution function based on central limit theorem. So you heard that before, central limit theorem in applied statistics course, but now you will show how is it, how you want to find the sampling distribution using the central limit theorem, CLT. All right, and then you should understand, you should be able to understand the concept of parameter, estimate, estimator and estimation. Okay, so that one actually you have learned this a little bit at applied statistic course. Okay, but now here you will learn how to get the value. All right, and then next you will derive parameter estimation using method of moment and maximum likelihood estimation. So method of moment you have learned in previous chapter, we just apply it and you can see later how is it. All right, but maximum likelihood estimation is a new thing for you and it's not complicated, but you must very good in differentiation. Okay, and then next is to derive the properties of good point estimator, including maximum variance unbiased estimator or MVUE. So basically here in applied statistics, you remember you have 4 properties of good point estimators. Okay, if you remember, we have unbiased, sufficient, efficient. Okay, and one more is what is it? Consistency. Okay, consistency. So 4 things, isn't it? So in previous course, you just say you know that. Okay, but in here, in this chapter, you will learn how to get the value, how to get the estimated. All right, and then last, to derive the interval estimation. This one similar lah. Actually, you have learned before. You just use the formula of the confidence interval estimation, isn't it? But in here, you learn how to get the confidence interval, how you get the formula. So this is the contents. So you can see that you have 5.1 until 5.7. But if you refer your textbook, this content is not in one chapter only. You will have it in chapter 7, chapter 8, chapter 9. Okay, so it's a combination of chapter. Okay, but when I do the notes too, I use the same number in the textbook, so it's easier for you to refer in the future. So basically for this chapter 5, if you refer your textbook, you will have from chapter 7. Yeah, 7, 8, 9, and is it 10 if I'm not mistaken? Let me see. No, 7, 8 and 9. Okay, so that is for chapter 5. So this is the content. So in this video, I will go for introduction first, okay, about the sampling distribution related to the normal distribution. So this is the motivation lah. Okay, so again, our objective of statistics is to make inference about a population based on information contained in sample taken from that population. So the concept is similar if you remember in applied statistics. Okay, in statistics usually we want to make inference about the population, but because of the population data is very big, it's quite difficult to get everything, to get all. That's why we use sample. So based on this sample, we will find, or we will calculate, we will analyze, then we will make inference about the population. So the preceding chapter plays a role in the development of statistical inference. That means from the previous chapter that you've learned in this course is very important. How you relate each other and how you develop the statistical inference. So the objective statistic as closely as the study of the distribution of function of random variables. So you can see in previous chapter you have, for example, u equal to y1 plus y2. So that is the distribution of a function of random variables. So in this sampling, it's quite similar. But now your y1, y2 is a considered sample. 1 sample, 2 sample, 3 sample and so on. Okay. So to estimate population parameters, okay, or to make decision about a population, a function of the n random observation that appear in a sample. So this is quite related with previous chapter, but in previous chapter maybe you only have 2, isn't it? y1, y2, y1 plus y2, y2 square plus y1, for example, a function of a random variables. But here we are talking about sampling. That means how many sample and random observation, how many sampling you get, and then this sampling, how to make inference, how to find the probability distribution function. So we can illustrate, okay, this is one example. So let's say consider the problem of estimating population mean. Okay, you have mu. So this is considered as a population. Okay, mu is a mean for population. So then we have let y1, y2 until yn, a random sample of n observation. Okay, so I consider all of you know small n is sample from the population. Then when you want to find the sample mean, you will have y bar. So what's the formula? y1 plus y2 plus y3 until yn divided by n. So basically you will have this one. Okay. So you use this one to estimate the mu. Alright. So this one, how good is this estimate? So it depends, okay, the behavior of the random variables, their effect on the distribution of y bar. Okay, because y bar is considered a sample mean, isn't it? So we will find this sample distribution function. Okay, so that's why you want to estimate population mean using y bar. But in order to make sure this y bar is very good or is good for estimate the mu, we need to find the sampling distribution for the y bar. Okay. So the goodness of this estimate depend on behavior of the random variable y1, y2 until yn, and the effect that this behavior has on y. Okay, this is y bar if I'm not mistaken. Okay. Okay, over yn. So I mean, you can see, you can check. I will check as well from the chapter 7 to the notation too. I think there is a mistake there. Y bar should be, all right. And then yeah, I think something missing there. Okay, it's okay. I will try improve that. Okay, however, we can determine the probability distribution of the estimator y bar. So in this chapter, we want to find this one, the probability distribution of the estimator y bar. Okay, because we know that when we want to find, I mean, we have mu. Mu is the population mean, but we want to estimate this one using x bar, or in our case here is y bar lah. Alright, so in order to know this y bar is good enough for mu, we will find the sampling distribution, or we will find the probability distribution of this estimator. Okay, if it's similar with this one, so it's considered it's a good estimator for mu. Alright, so to determine the probability distribution for a function of n random variables, this one, okay, so we must find the joint probability distribution function for the random variable themselves. So in here, we have y1, y2, y3, yn. So we will find the join lah. So that's means if we want to find the join, we will have y1, y2, y3 until yn. Okay, so how to join, you have learned before in previous chapter. Okay, so that's why I said previous chapter is very important in order for you to do this chapter. All right, so I think Is it that's all first? Wait. Okay, so now we move to introduction. Okay, by definition 7.1. Okay, a statistic. Remember this one you have done before as well in applied statistic course. We have a statistic. Okay, it's a function of the observed random variable in a sample and known constant. So remember before this you have x bar. So x bar is a statistic. Mu is a what? Parameter. So similar in this context or this chapter, a statistic is a x bar. Okay, it's a function of the observed random variable in a sample and known constant. Okay, it's a value. So you have learned many statistics. Okay, you have learned many statistics. For example, the sample mean, sample variance, and then you have a y(n) ordered, which is from maximum from this all, and then you have y first ordered is minimum of this one, and then you have learned range, okay, and then you have sample median and others. Okay, actually you have this before in applied statistic course, okay, but this one you learn here. All right, here. So all this is a statistic. Okay, it's a value of a function of random of a function of the observed random variable. All right, so here if you look, okay, again statistics are used to make inferences, okay, to estimate or decision about unknown population parameters. Okay, and then because all statistics are function of the random variable observed in a sample, all statistics are random variables. Okay, why we call it a function? Because for example, when we want to find the sample mean, you must have a function that we how to get mean, which is y1 plus y2 plus y3 until yn, isn't it? So that calls a function that you learned in previous chapter. You have, for example, u equal to y1 plus y2. So this is a function, isn't it? But in this chapter, because you use sampling distribution, sample function, so in order for you to have sample mean, so sample mean, you will get y1 plus y2 plus until yn divided by n. So you will get sample mean. So this is called a function as well. All right. So consequently, all statistics have probability distribution. Okay. So when all these statistics have probability distribution, then we call it sampling distribution. Okay. We not call it probability distribution. Usually this one we use for population. But here, because it's come from statistic, we call it sampling distribution. Okay. So the sampling distribution of a statistic provide a theoretical model for the relative frequency histogram of the possible values of the statistic that we will observe through repeated sampling. Okay, so we do many repeated sampling. I will show you by example here. Okay, so look this example 7.1, page 347. So let's say you have a balanced die, is tossed 3 times. So you know that when we have one die, you have how many outcomes? 6 outcomes. But this one you toss how many times? 3 times. So let y1, y2 and y3 denote the number of spots observed on the upper face for tosses 1, 2 and 3 respectively. So that means y1 for first time toss, y2 is second time toss, and y3 is third time toss. Okay, so suppose we are interested in y bar. So y bar is a mean of the sample. So we have y1 plus y2 plus y3 divided by 3 because we have 3 times. Okay, so the average number of spots observed in a sample of size 3. So the question asks, what are the mean? So in here, in order for us to find the y bar mean, we denote like this. Okay, mu sub y bar and standard deviation sigma y bar of sample mean distribution. Okay, so how can we find the sampling distribution of y bar? All right, so how is it? So if you look here, okay, so you can show, okay, this is based on exercise 3.22. You can refer back. Okay, so based on this one, you can find that the mu is equal with expected yi equal to 3.5 and sigma squared, or we call it variance yi equal to 2.9167. Okay, so I is from 1 to 3. So since y1, y2, y3 are independent random variables, the result derived in example 5.27 using theorem 5.12 implies this equation or this number. So if you look here, how can we derive the distribution of the random variables y bar? So the possible values of the random variables, let's say W, okay, equal with y1 plus y2, y3 are 3, 4, 5 until 18. And y bar will be equal with W divided by 3. Okay, because how many times tosses? 3 times. Okay, and then because the die is balanced, so each of the die will give you outcome 1, 2, 3, 4, 5, 6. All right. So how you want to find the possible outcome? 6 power 3. So you will get 216 distinct values of the multivariate random variable of y1, y2, y3 are equally likely. So basically, the probability of distribution for y1 equal to y1, y2 equal to y2, y3 equal to y3 will give you like this. All right. So each of the possible outcome, okay, equally likely will be 1 over 216. Okay, so your yi 1, 2 until 6, and then I from 1 to 3 as well. Okay, that's mean each die you have 6 outcome lah. So how many die or how many tosses you done? 3. So that's why you have 1 until 6 3 times as 3 times. Okay, right. So for y bar, okay, equal to 1, you will have PW equal to 3. Okay, that's mean you have each of y. Okay, this one, remember you have y1, y2, y3. Okay, so you can do the tree diagram as well. You have first 1, 2, 3, 4, 5, 6. And then you have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then each here also 1, 2, 3, 4, 5, 6. That's why total here is 1 over 216. Okay, for each here. So that's mean if you have 1, 1, 1, 1 over 216. And then if you have 1, 1, 2, 1, 2, 1, this is all the possible. So you will get this value. Okay, you can do this. Okay, so the probabilities for y bar equal to I over 3. Okay, so here I is from 7, 8 until 18 are obtained similarly. Okay, so here you can see from the figure. Okay, actually this one can be done using the the applet tool. Okay, if you look we have the software. I attach the link of the software to in your column. Okay, so you can see here. Okay, this one a simulated sampling distribution for y bar. Okay, from example 7.1. That's mean how many outcome you have for one die. You have 6 outcome. Okay, and then you have how many tosses? 3 tosses. So you can see here. All right. The frequency. All right, the frequency. And then if you look B is the mean and standard deviation of 4,000 simulated values of y bar. So you can see here when we do the number of rows 4,000 times of size 3, you get 3.495 for the mean, and standard deviation is 0.981. Alright, so this is one standard deviation, 1 sigma, 2 sigma, 3 sigma, you can get this value. Okay, so here you should understand that we have y bar. Okay, y bar equal to y1 plus y2 plus y3 over 3. So this y bar we repeat for 4,000 times. Okay, 4,000 times. Then you get this mean. So this actually mu for y bar. And then this is standard deviation for y bar. Okay. Right. So I do hope that you understand the sampling distribution. Okay, but it's quite similar with applied statistics. Okay, the theoretical part. And I believe you are my student in previous class. I did mention this one. Okay, but here in our class, in this semester class, we want to find the sampling distribution for the y bar. All right. Okay. So I think that's all for this one. We'll continue for more in next video. Thank you.